My guest again today is Ned Nikolov.
Well, today I would like to follow up on an aspect of my presentation that I gave about a month ago. And there I talked about a number of things, but one of the things that I mentioned only in a couple of slides, if I remember, was the definition of the greenhouse effect and what the greenhouse gas radiative forcing is. And there is a lot of confusion on this topic, and scientists that are, with PhD degrees, they don't understand. Apparently, they don't understand what actually the definition of the greenhouse effect, the way it has been used in science and in textbooks and papers and so forth, and also radiative forcing, actually is physically meaningless. And that's what we're going to talk today. So the title of my presentation is the ill-defined greenhouse effect and greenhouse gas radiative forcing in climate science. I am listening here also my co-author, Carl Zeller, who is not here right now, but we've been doing this work together for many years, so I'm putting his name on as well. So the definition of the greenhouse effect. Well, in my last presentation, I mentioned that there are two definitions. One is through the difference in temperatures between Earth with atmosphere and Earth without atmosphere or without greenhouse gases. And the second definition, which actually is considered to be the core or the more relevant and important definition, is through the radiation. And this slide shows the radiation budget of Earth that comes from IPCC. And the greenhouse effect has been defined for the first time in the context of this slide, has been defined for the first time actually by Ravel and Ramanathan in 1989. They established a project for the first time, asking money from NASA, and they got actually the grants to measure those fluxes of long-wave radiation coming from the surface and from the top of the atmosphere. And their definition of the greenhouse effect was the difference of the long-wave flux between surface, which in this graph is 398 watts per square meter, right here on the bottom, and the top, which is about 239 watts. Roughly it's 240 watts. So a difference of 159 watts of this flux is considered to be absorbed by the atmosphere, specifically by the greenhouse gases, and that absorption is called the greenhouse effect. That's the radiative definition, formal radiative definition of the greenhouse effect. Now, the assumption here is that this attenuation of the flux from 398 to 239 that is observed in the troposphere is actually a result of the absorptive abilities of the greenhouse gases, and it's a heat that is being kept or trapped in the atmosphere, which causes basically the Earth's surface to be warmer than if you didn't have any greenhouse gases or any atmosphere on the planet. So I'd like to show here the paper that was published in 1989 by Ravel and Ramanathan. This was in Nature. And the title is Observational Determination of the Greenhouse Effect. And the first sentence in the abstract reads, satellite measurements are used to quantify the atmospheric greenhouse effect, defined here as the infrared radiation absorption trapped by atmospheric gases and clouds. This is exactly the difference that I mentioned before. However, one thing that I want to point out here in the very beginning is that in addition to the long-wave flux, we also have convective fluxes, which are non-radiative, yet they are still energy. They're measured in watts per square meter. Those are fluxes of sensible and latent heat flux that are shown here. 84 watts per square meter, I think, is the sensible heat flux. The latent heat flux, I'm sorry, and the sensible heat flux is 20 watts per square meter. So together, they add to about a little bit over 100 watts per square meter. Now, this is a small flux compared to a long wave, yet it's about 20% of the total flux, but it has to be considered when you're discussing the attenuation and what's causing this attenuation through the troposphere of the surface fluxes. And in this presentation, I will show that this attenuation has nothing to do with the infrared opacity or non-transparency of the atmosphere, as it is claimed in climate science, and has everything to do with adiabatic cooling of ascending air currents that are the cooling that is caused by the decrease of pressure with altitude, a mechanism that has nothing to do with greenhouse gases. So this is those are the abstracts of two papers that were not published, but they have been in circulation for several years by Weingarten and Happer. I always have a problem pronouncing this name. He's Dutch, I suppose. And those papers, they are interesting papers, and they should be published, I think, because if people refer to them, it's important to be published instead of be in form of manuscripts. But those papers are written by skeptics. And the reason I'm using those papers is that to show that the skeptics firmly believe in that definition of the greenhouse effect and radiative forcing that's actually in the mainstream science. There is no dispute about that something is wrong with that definition. So, for example, the first paper, 2019, in the introduction, we see the following statement. The greenhouse warming of the Earth's surface and lower atmosphere is driven by radiative forcing, F, which is the difference between the flux of thermal radiation energy from a black surface through a hypothetical transparent atmosphere and the flux through an atmosphere with greenhouse gases, particulates, and clouds, but with the same surface temperature. If you think about it, it's a little bit convoluted way of saying that. So basically, they assume that if there is no greenhouse gases, the energy flux that's coming from the surface will not attenuate and will reach with the same intensity to the top of the atmosphere, the same intensity as the intensity of being emitted from the surface. If you compare this with the current situation where we have greenhouse gases and this flux has been attenuated, like we showed in the previous slide, from talking about infrared radiation specifically only, from 398 watts per square meter to about 239. That attenuation, basically, what they say in this sentence is what they call a greenhouse forcing, radiative forcing. However, this is basically the definition of the greenhouse effect. So they use a little bit different terminology, but it's the same thing. And the paper from 2023 has very interesting statements here, and it's more clear because there is one statement, this is actually towards the end of the paper. They say for a gray atmosphere, surface radiation to space is attenuated by a factor of e to the minus tau sub zero, where tau sub zero is the vertical optical depth from the surface to outer space. So basically, they are assuming that this radiation flux coming from the surface is attenuated because the atmosphere is opaque to infrared radiation. Absorbed surface radiation is replaced by radiation emitted by the greenhouse gases higher in the atmosphere. The other important sentence here is without greenhouse gases, the adiabatic temperature profile of the troposphere will evolve into an isothermal profile with the same temperature as the surface. So in other words, they say that the so-called lapse rate, that's a term that is used to describe the drop of temperature with altitude in the troposphere, which is about 6.5 degrees of Kelvin or Celsius per kilometer. They say that this lapse rate will be zero. That's another way of describing this. And then they say greenhouse gases increase the temperature of the surface compared to the surface temperature in an atmosphere without greenhouse gases. So their whole idea here is absolutely no different. Those two skeptics, they have absolutely no different idea from what is in the mainstream climate science from what is in the greenhouse theory. And using this definition, they reach the conclusion that greenhouse gases, which in Earth's atmosphere are trace gases, they actually control the surface temperature, which we will see that it is not correct. If the definition of the greenhouse effect and the radiative forcing as formally defined in the literature is physically incorrect, that means that the entire concept falls apart. This is a screenshot from a website of MIT, Massachusetts Institute of Technology, and it's called Climate Portal. And here they define radiative forcing, which is more of a standard definition of radiative forcing, unlike Happer's definition, which is basically they define the greenhouse effect. Here, the radiative forcing is defined like this. Radiative forcing is what happens when the amount of energy that enters the Earth's atmosphere is different from the amount of energy that leaves. If more radiation is entering Earth than leaving, as it is happening today, then the atmosphere will warm up. This is called radiative forcing because the difference in energy can force changes in Earth's climate. Okay, so what they're talking about here, another term for that, it's called Earth's energy imbalance, or EEI, okay? So the notion is that under ideal conditions, so pre-industrial conditions, they actually talk here on the second page, the changing balance. They say that in the pre-industrial times, starting about 1750, when the carbon emissions were almost none, the human carbon emissions I'm talking about are almost non-existing, then the system was in equilibrium, and the amount of incoming radiation from the sun was equal to the amount of long-wave radiation going out to space. So under those conditions, the temperature is not changing. And they say, compared to this baseline, radiative forcing can directly measure the ways recent human activity have changed the planet's climate. The biggest change has been the greenhouse gases we have added to the atmosphere, which keep heat from escaping the Earth. This is a very key sentence that actually describes in very clear fashion the belief system that the atmosphere can trap heat, and the trapping of heat is caused by the so-called greenhouse gases, which absorb and emit long-wave radiation. And so the imbalance that occurs at the top of the atmosphere, according to this theory, according to this understanding, is caused not by anything else, but by the fact that we have increased amount of greenhouse gases in the atmosphere, which trap more heat, and they prevent part of the long-wave radiation to escape from Earth, and therefore it creates an imbalance where more solar radiation is coming in than long-wave radiation going out. And that's causing the climate change. So in the view of the standard climate science, it is the energy imbalance at the top of the atmosphere that's controlling the climate system, not what's happening on the surface. This is a very important point. So before we go and explaining why this definition is physically flawed, we need to make a little bit of detour and talk about some fundamental stuff in thermodynamics, which are related to our explanation. So the first thing we're going to talk about is the ideal gas law for atmospheric gases under most conditions. This slide shows two forms of the ideal gas law. There is a molar form, which is considered more generic, so to speak, and there is a mass form. The molar form is basically pressure times volume equals the amount of gas in moles times the temperature and times the universal gas constant. So basically the law says that the product of pressure times volume is proportional to the amount of gas and its temperature. Okay, the important thing is here to note that the product pressure times volume equals actually energy. This is the thermokinetic energy of the gas that gives the gas its temperature, because the pressure has units of force per unit area. Volume is basically a cubed distance, right? So when you combine those numerically, you end up with a force times distance, which is the definition of a joule. So the pressure times volume is actually the energy content, thermal energy content of the gas. The mass form of the gas, it arrives when instead of moles, you use actually the mass of the gas measured in kilograms, right? In this case, you have to use a specific gas constant, which is the universal gas constant divided by the molar mass of the gas, shown here on the right-hand side. And there is also another definition, which is called Meyer's relation, which is very interesting. that the specific gas constant also equals the difference between specific heat at constant pressure minus the specific heat at constant volume. Now, specific heat for any gas is basically the amount of energy that is required to raise the temperature 1 kilogram of gas by 1 degree Kelvin, okay? The reason why there is a difference between specific heat at constant pressure and constant volume is that when the pressure is constant, the volume is not. And so when you add heat to a gas, the volume expands, which causes it to cool a little bit. So it requires more energy per kilogram of gas to raise its temperature by 1 degree, because it takes a little bit more heat in order to do that, compared to when the volume is constrained, is fixed, like the C sub V is the constant volume. In that case, the energy required to raise the temperature of 1 kilogram of gas by 1 degree is less, because there is no expansion in volume. That's a very key difference. So, okay, so the mass form, we're going to be using later in the presentation, the mass form of the gas law. But basically, it says the same thing, that the kinetic energy of the gas that is given by the product of pressure times volume equals the mass of the gas and is proportional to its temperature, and the proportionality constant is called specific gas constant, in which case it is specific and different for every gas. The universal gas constant is not specific for individual gases. That's why it's called universal, because it applies to all kinds of gases. And here you can this is the most fundamental equation that in thermodynamics, and you can see that in none of those two equations there are any parameters that define the radiative properties of gases. There is nothing about related to their infrared absorptivity or emissivity. You just have pressure, volume, amount of gas, and temperature, okay? So another concept that is very important here later in deriving some of those equations that we're talking about is this atmospheric hydrostatic equilibrium. Now, in order to have an atmosphere, a stable atmosphere, which means the atmosphere is not instantaneously collapsing to the surface or instantaneously being dispersed in space, you need to have a balance between the force of pressure, which is directed outwards. This is the blue arrows, and the gravity, which is directed inwards. At every layer in the atmosphere, if we have this balance, and we have this balance more or less, it's not precise, but we have this balance, then the atmosphere is relatively stable, and there is no collapse, and there is no dispersion in space. Now, it doesn't mean that the Earth is not losing atmosphere. We're losing about 90 tons of atmosphere a day, but overall, because of the huge mass of the atmosphere, 90 tons a day is a very small amount. And overall, the atmosphere is stable, at least on time scales of hundreds of years, maybe to a few thousand years. So this hydrostatic equilibrium is defined mathematically with this equation, dP dz, which is the change of pressure with altitude, equals the negative product of density rho times the gravitational acceleration, okay? The derivation of this equation is very straightforward, and it's in all the textbooks. And so just for the sake of time, I will not go to this derivation here, but just if you take my word, and you can Google hydrostatic equilibrium, you'll find the same equation everywhere pretty much you look at. So dP dz equals minus rho times g. Now, this equation, hydrostatic equilibrium equation, is the basis for the derivation of the equation that describes the change of pressure with altitude. It's called barometric equation. That equation is very important for our discussion. So I'm going to go real quick along the path of its derivation. Now, it's a little bit of a math, and if you don't feel that you don't understand it, you can just, close your eyes for a minute, and it'll go away in a couple of minutes. But here we go. So here is the first original equation that defines in differential form the hydrostatic equilibrium. Here we can, from the gas law, we can express the density of the air using the gas law. We can express it as a product of pressure times the molar mass divided by the universal gas constant times the temperature. This comes straight from the mass form of the gas law. if we insert that equation into equation 1, insert equation 2 into equation 1, we get equation 3, which has this form. And then what we do is we separate the variables. We put all the p variables on one end and the z variables or the altitude on the other end. So we have dp over p equals minus mg over rt times dz, okay? Then we replace the temperature with a linear function that shows the change of temperature with altitude. In this case, L is the lapse rate, which means the rate of change, and Z is the altitude. And so T sub 0 is the surface temperature, right? So the temperature at any height in the atmosphere, T sub Z equals T sub 0 plus the lapse rate times the altitude. If we replace this in the above equation, and then we can integrate both sides, one over P and the other one over the altitudes, and then we arrive at the logarithmic equation of this form. Then we solve this equation we take anti-logarithm and solve this equation for P sub Z, which is basically the pressure at altitude Z, and we get this formula. This is the full barometric equation that describes the change of pressure starting from the surface that has a value of P sub 0 to any altitude with high at altitude Z in the atmosphere, and this equation will describe that. And as you can see, it's a function of surface pressure. The pressure at any given latitude is a function of surface pressure, is also a function of the surface temperature, and it depends on gravity, and it depends on the lapse rate. Okay. Now we'll see. The interesting thing here is that this formula applies when the lapse rate is different than 0. If the lapse rate is 0, then the solution is a little bit different. And has this formula, which is, it shows that there is an exponential decline of the pressure, even though the lapse rate is 0. That means the atmosphere is assumed to be isothermal, which is not in reality. In reality, there is no isothermal atmosphere in the troposphere going up. The temperature always drops. So here is a graph that illustrates the barometric formula when applied at different levels of pressure. And you can see that the pressure basically drops with latitude exponentially. The interesting thing here to note is that the effect of the lapse rate, and we have 3 cases here. Red is a dry adiabatic lapse rate, which is minus 9.8 Kelvin per kilometer. Green is humid air, which is about the environmental lapse rate, 6.5 Kelvin per kilometer drop. And moist air is really like air that is close to 100% humidity, and it has only a drop rate of 5 Kelvin per kilometer. And you can see the differences between those 3 scenarios, different lapse rates. It only occurs at high altitudes, and it's nothing compared to the overall exponential decrease of pressure, which tells us that the main factor for the decrease of pressure with altitude is this condition of hydrostatic equilibrium, which was the starting point for the derivation of this equation. So that's very important to remember. Now, we're going to be talking about our class of thermodynamic processes, which is a very broad class called polytropic processes. Those are processes that involve the transfer of work and heat between systems or gas systems. And the transfer of work and heat is done in such a way that some properties of the system remain constant. And it turns out that pretty much all thermodynamic processes that are out there, they follow one way or the other this polytropic pattern. So the word polytropic, it means exactly that, processes that are transferring work and energy, and where some of the properties remain constant. The definition of the polytropic process in thermodynamics, and you can find this in any textbook, is this equation: P times V to the power of N equals a constant. So this is pressure times volume to the power of N. N is the polytropic index that can take wide range of values. basically from minus infinity to plus infinity, okay? However, the good news is that in the atmosphere, the range of values that this index takes is pretty limited. So before I go into those details, let me point out that when you have a polytropic index, for example, of 0, that means pressure, because the volume disappears, the volume becomes 1, right? If n is 0, the power term is 0, then volume becomes 1, and then pressure equals constant. That's called isobaric process. That means process that occurs under constant pressure. Now, in the atmosphere vertically, we don't have that, because we saw that the pressure in the atmosphere drops as a result of a hydrostatic equilibrium, right? So when the polytropic index equals, for example, 1, then you have PV equals PV. So PV is constant. That means because PV is proportional to temperature, that defines a isothermal process. That means process that occurs where the temperature is always constant. So for n equals 1, PV, the polytropic process becomes isothermal. For values of n greater than 1 and smaller or equal to the ratio of specific heats of a gas, C sub P divided by C sub V, in that range, we're talking about quasi-adiabatic processes. And when the polytropic index equals specifically this ratio, C sub P divided by C sub V, it's called adiabatic index. So then we have a fully adiabatic process, also known as isentropic process, because it's a process that it's adiabatic, but it's fully reversible. So the entropy is 0 when you do the cycle, okay? So in the Earth's atmosphere, C sub V and C sub V, those specific heats, they are specific to every gas. In the Earth's atmosphere and with our current composition, that ratio equals 1.4. So in the Earth's atmosphere, the polytropic index is typically greater than 1, which means the atmosphere is not isothermal, and equal, smaller or equal than 1.4. So the atmosphere is somewhere between isothermal and fully adiabatic, but it's more into the adiabatic than it's not isothermal, right? It's more adiabatic. So I call it a quasi-adiabatic. So this is a graph that illustrates the relationship between volume and pressure under different values of n. When the n has values that define, different types of system, like I said, isobaric, isothermal, isochoric. Isochoric is a constant volume, for example, and that occurs when the value of n is in infinity, which we don't have that in the atmosphere either, because the atmosphere is free to expand and the volume of the atmosphere changes depending on the degree of heating. This is why the tropopause is found at about 18 kilometers in the tropical region over the equator, and it's about only like 8 or 9 kilometers in the poles. That's because the heating in the tropics is much higher, and therefore the volume of the atmosphere is higher, and the atmosphere extends actually at a higher altitude. So anyway, this graph that gives you this illustration when this index P times V to the power of n is constant, how the relationship between volume and pressure changes when you have different values of the polytropic index. So because the volume, according to the gas law, the volume of a gas is proportional to the ratio of temperature over pressure, we can express the polytropic process also in terms of pressure and temperature. And if you substitute T over P in the above equations where you have a volume to the power of n, and then you do the math, basically it's very simple, you get another version of the polytropic process, which says pressure to the power of 1 minus n times temperature to the power of n equals a constant. Now, this is the equation we're going to use. We can use actually to derive, a universal polytropic relationship between pressure and temperature in the troposphere or in the atmosphere in general. To do that, because by definition this is a constant, so we can say that at altitude elevation z, the product of pressure to the power of of 1 minus n plus temperature to the power of n equals those equivalent quantities at the surface, right? So this is the equation. That allows us to algebraically derive an equation that describes the temperature at any altitude z as a function of surface pressure, the pressure at this altitude z, and surface temperature. And here is this equation. So T sub z equals T sub 0 times the ratio of the two pressures, the pressure at the altitude z and the pressure of the ground, raised to the power of n minus 1 over n. Okay. So in order to have a adiabatic version of this equation, so this equation describes, like I said, a broad relationship between temperature and pressure in any gas system. And in the atmosphere, like I said, the value of index n is limited to the values, to the limits of 1 to 1.4, right? So when the value of the polytropic index n is 1.4, then we have a adiabatic process, and we can use that general equation to derive this equation by substituting the n with the ratio of the specific heats, and then accounting for the fact, the minus relation, that the specific gas constant of the air is the difference between the specific heat at constant pressure and specific heat at constant volume. This is the one the relationship that we saw in the previous slide. So by doing that, here is the equation we get for that describes the in adiabatic conditions, in adiabatic process, it describes the relationship between the temperature at altitude z and as a function of pressure of this altitude z, the pressure of the surface P sub 0 and the temperature of the surface T sub 0. And then the power term has changed after we do the algebraic manipulation of the n. Like I explained, it changes basically to a ratio of specific heat of the atoms of the air divided. I'm sorry, the specific gas constant of the atmosphere divided by the specific heat of the air. And it happened to be that this ratio actually equals 0.286. So now let's see what the dry adiabatic lapse rate, how it is derived and what it means. So as I pointed out, the adiabatic lapse rate, which is mentioned by Happer, and they use it a lot in climate science, is basically the change of temperature with altitude. But this change, like I said, is not, the rate of change is not fixed. There are different types of adiabatic lapse rates. And so here we're going to talk about the dry adiabatic lapse rate, which is kind of the backbone of any lapse rate, simply because it defines the neutral stability conditions of the atmosphere. When the actual adiabatic lapse rate is they call it also environmental lapse rate. If it's less than the dry adiabatic lapse rate, the atmosphere is considered to be a little bit stable. And if it's higher than the adiabatic lapse rate, then it's called unstable, which promotes a lot of convection, convective storms, and so forth. So the derivation of the dry adiabatic lapse rate, because we saw already that the temperature is a function of pressure in the atmosphere, and at the same time the pressure is changing with altitude, because that change is driven by the hydrostatic equilibrium requirement, right? So basically, the lapse rate could be defined and is defined as dT dz, the change of temperature with altitude, equals the change of temperature with pressure, dT dP, times the change of pressure with altitude, dP dz. So we need to find those two derivatives, because the product of those two derivatives will give us the actual adiabatic lapse rate. So in order to do that, first of all, we already talked about that the hydrostatic equilibrium condition requires that the derivative dP dz equals minus density of the air at a given altitude times the gravitational acceleration. So minus rho times g. In order to derive an expression for the the TdP, the derivative of temperature with respect to pressure for adiabatic conditions, we can use the formula that we saw in the previous slide that defines the relationship between the temperature at a given latitude and the pressure level at latitude to the temperature and the pressure of the surface. This is the equation that you see over here. And when this equation is differentiated, we find the first derivative with respect to pressure, we get this expression over here, which after simplification, it basically becomes the TdP equals the product of specific R sub C, which is the specific gas constant, times the temperature divided by the specific heat at constant pressure times the pressure. Well, we can simplify this equation even further by considering that according to the gas law, the temperature of a gas is basically a product of pressure divided by density times the specific gas constant. If you replace T over here in this equation up here, we get the final expression for the derivative of temperature with respect to pressure for adiabatic conditions. And that becomes the TdP equals 1 over rho times C sub P, okay? So combining this equation here with the hydrostatic equilibrium condition, you multiply those to get this term, we get actually a very simple expression for the adiabatic lapse rate, which is minus G over C sub P, which means that's the ratio of gravity divided by the specific heat of the air at constant pressure. Now, like I said, this is the backbone of the lapse rate in the Earth's atmosphere and any other atmosphere. This is a general equation you can find in any textbook. If you just Google adiabatic lapse rate, quite often they just give you this equation without going to this derivation. I just wanted to show the derivation that is based on solid thermodynamics. It's not just a made-up equation. And so for the Earth's atmosphere, this adiabatic, dry adiabatic lapse rate, when you substitute the values for gravity, which is 9.8 meters per second for the gravitational acceleration divided by the specific heat at constant pressure, which is about 1,005, you get minus 0.0098 Kelvin per meter, or multiplying by 1,000, you get 9.8 Kelvin per kilometer. This is the rate of drop of temperature in the troposphere if the conditions are neutral, stability conditions are neutral, okay? So what about when you add water vapor? Well, then it becomes something that is known as the moist unsaturated adiabatic lapse rate. This is the lapse rate when you have added some water vapor, but its relative humidity is not 100%, it's less than 100%, between 0 and 100%. Then you have a different formula for that lapse rate. And this formula is like this, and basically it has a correction term. If you can see here, the standard adiabatic lapse rate is given by gravity and the specific heat, but then this whole thing is multiplied by this correction term, which depends on the water vapor mixing ratio in the atmosphere. And this ratio is given by this expression here, which is a function of vapor pressure and total pressure. But the result is that the lapse rate, the moist unsaturated adiabatic lapse rate, decreases, okay? So that means we have now lesser of a steep drop in temperature. Normally it's about 6 degrees per kilometer instead of 9.8 degrees, which is why the atmosphere on average is known in Earth's atmosphere, because of the presence of water vapor, is known to be marginally stable, okay? So it has some stability that is, it's more stable than neutral. So if you add more water vapor and make it basically the air, you make the air saturated, then you have a moist saturated adiabatic lapse rate, which has a different formula, and just for simplicity, I'm not going to give it here. But that rate is about 5 Kelvin per kilometer decrease. So in general, what we have here, as we adding water vapor to a dry air, we have this relationship. The dry adiabatic rate is typically larger than the moist unsaturated adiabatic rate, which is larger than the moist saturated adiabatic rate, okay? Now, this is very important because greenhouse, the water vapor is considered to be the most powerful greenhouse gas. According to the standard climate science, and including the skeptics like Happer, they believe that without greenhouse gases, like I pointed out, the atmosphere will be isothermal. That means the lapse rate will be 0. However, the thermodynamics of the atmosphere, the way I show it here, which are standard equations that you can find in textbooks, and it's a standard atmospheric physics, it actually shows the exact opposite effect. By adding water vapor, specifically, the lapse rate actually becomes smaller, not larger. And so adding water vapor moves the troposphere towards isothermal conditions, although those are never reached fully, but it moves it in that direction. So that's exactly opposite of what has been assumed in climate science and by people who actually think and believe that greenhouse gases are the cause for the lapse rate. And as we see here, you know, this lapse rate, the moist unsaturated lapse rate is actually kind of the general lapse rate that occurs most often in the atmosphere. And you can see here that there is no term that defines any infrared radiative properties of gases. We have the specific heats of a gas under constant pressure and constant volume. Actually, you don't have a constant volume. You have a specific heat of the air, of the dry air, compared to specific heat of water vapor at constant pressure, right? And then you have the water vapor mixing ratio as a term in there, but you don't have anything related to infrared emissivity or absorptivity of the gases. In other words, this equation shows that the only effect, the only gas that has, trace gas that has an effect on the lapse rate is actually water vapor. And that's because when the water evaporates at the surface, it cools the lower portion of the troposphere. It moves up in the convective current, and then at some point it condenses because it reaches cooler environment. It condenses, and when it condenses, it releases the heat that was absorbed to the surface. So it transports the heat from the surface to the higher altitudes, and that causes the lapse rate or the decrease of temperature with altitude to decrease, to go in the direction of isothermal, okay? This is very important. So the CO2 has no such effect because CO2 is not a condensing gas. And thermodynamically, the CO2 is no different than nitrogen and oxygen. So, okay, we talked about the relationship here of the different lapse rates. Now, this graph illustrates the fact that you can use the polytropic process to derive a general equation that relates the relative thermal energy in the atmosphere to different pressure levels. So in this case is the ratio, if you look at this this formula, P times V, like I mentioned before, it's the thermokinetic energy of the gas. And so here we have a ratio of the thermokinetic energy of the gas at certain altitude, Z, as a fraction or divided by the same ratio at the surface, okay? So this is the relative decrease, the relative change in atmospheric thermal energy as you go up in altitude, different pressure levels showing on the left, and altitudes in kilometers are showing on the right, okay? And we have three scenarios. You have dry air, we have a humid air, which is basically unsaturated, and you have moist air, which is saturated. The case that occurs mostly in nature, basically on the globe on average, is this one that has a lapse rate of about 6.5 a Kelvin per kilometer. And you can see here that the polytropic index changes from 1.4 for dry air to 1.17 for moist air, okay? And those curves are quite different. However, the common thing is that they all show decrease of the relative thermal kinetic energy of the atmosphere with altitude or with pressure levels. That decrease is very important because this is the one that drives the attenuation of the surface flux as it goes to the troposphere. Okay. So here we come back to the same diagram that I showed before. This is a little bit newer version. This is from the latest IPCC report from 2021. And on the left-hand side, you see the standard diagram, the way it's presented in the IPCC report. And then you have a little addition on the right that is not in the IPCC report, but it's very important to explain. And it's basically an omission, in the IPCC report, because they did not mention that this decrease, this attenuation of the surface flux is caused basically by the drop of pressure with altitude. And in this case, I pointed out the graph on the right. I point out that the total surface flux is not 398 watts, but 501 watts. And because here I have added the sensible and latent heat fluxes, which are non-radiative, but yet they're energy flux and they're coming from the surface. So you have a total surface flux going out of 501 watts per square meter, which at the top of the atmosphere, when it gets out to space in form of long-wave radiation, it's only 239. So the ratio of the top of the atmosphere flux to the flux of the surface is 0.477. In other words, about 52% of the energy flux coming from the surface has been lost in the while it's going to the troposphere, and it's not absorbed by greenhouse gases, but it has been adiabatically dissipated because this flux goes through progressive layers of lower pressure with lower energy, and when the convective current goes up, the air expands, and in the process of this expansion, it loses energy because the expansion is quasi-adiabatic. The volume increases, the pressure drops, and it causes the temperature to drop and the energy to drop. And so because the long-wave emission to space occurs not from the surface, but for the most part, it's in somewhere in the middle of the troposphere, anywhere between 5,100 and 5,700 meters above the sea level, right? That's called effective emission height, right? So the temperature at that level in the troposphere corresponds actually to a flux, a long-wave flux that is being seen coming out when you measure things from space, like from the Sirius satellite, right? So this attenuation of the flux is actually a result of this drop of pressure, which is associated with drop of thermal kinetic energy in the atmosphere. And we're talking just about a dissipation of this flux, not that the energy basically gets adiabatically dissipated, which means it goes into, the thermal energy is getting converted into work that does the expansion of the air, okay, of the parcel. And in our 2024 paper last year, published in August of last year, we have shown here, and I'm showing here on the right with a few equations, how you can reproduce almost exactly this, I call it, I use the acronym, I could not see here from the screen, EFAC, or TFAC, I'm sorry, TFAC. So it's tropospheric energy attenuation coefficient, phi, okay, I call it phi. And this is the ratio of 239 divided by 501. And this ratio gives you, this calculation gives you a ratio of 0.477, right? You can reproduce this ratio by using the polytropic relationship between temperature and pressure that we discussed in the troposphere, and combining this with the barometric temperature. So you have a change of temperature with the pressure, and then you have the change of pressure with the altitude. When you combine those two equations, you come up with this formula down here, which exactly reproduces the emission height of about 5,300 kilometers, reproduces exactly this ratio of TFAC, okay? So in other words, this is a proof that using the thermodynamic equations that this attenuation of the flux that we observe here in the real world has nothing to do with absorptive properties of greenhouse gases. You know, they're infrared radiative absorptive and emissive properties. On the bottom here, you can see the link to our latest paper that describes all this. There is a URL, and it's open access, so people can download it easily. So the definition of the greenhouse effect has been physically incorrect because it's based on using non-existing energy. This is energy that has been dissipated in ascending air currents from the surface to the top of the atmosphere, energy being lost due to the decrease of pressure. And so you would expect that this definition will not produce good results in terms of quantifying the actual thermal effect of the atmosphere. And that's the case here in this slide. We show the map on figure 1, which is the lower left. It's basically that difference of the long wave flux from the surface and the top of the atmosphere. And you can see that this is a spatial representation. It's a geographic map. You can probably barely see the continents. I can see them, but the continents are here in gray. And it basically shows that around the tropics, you have the highest absorption, so-called absorption of this energy. It's not absorption. You have basically the highest dissipation of this energy around the tropics. And around the poles, this quantity is the smallest. Well, if you compare the temperature profile of Earth to that of the temperature profile of the moon, which gives you the actual thermal effect, quantifies the actual thermal effect of the atmosphere, you will see that it follows the exact opposite pattern. The highest difference, the largest difference between the Earth's and Moon's temperature is at the poles, and the smallest difference is at the equator. So this illustrates, that this index that's being used to define the greenhouse effect not only doesn't have any physical basis, but it just produces a nonsense. The same thing of Antarctica. There has been a couple of papers that were published over the last, first one I think was 2015, and then another one in 2018, I believe. What's the year here? 2015, yep, and 2018, where different teams using that matrix of defining the greenhouse effect as a difference in fluxes between surface and top of the atmosphere, over Antarctica, they found that this produces negative greenhouse effect. Negative. It's like, what the hell that means, If it's negative, that means it's non-existing. Well, that would imply that the Antarctica would have the same temperature as the south pole of the moon, because the moon has no atmosphere, has no greenhouse effect. So therefore, that's the conclusion. However, that's not the case. Antarctica, central part of Antarctica, is about 140 degrees warmer than the south pole of the moon. So that tells you, that's another example that tells you that this definition is just nonsensical. Okay, so now we're moving to the radiative forcing, or also known as Earth's energy imbalance. Those graphs show the calculation of the radiative forcing from Sirius data. Sirius is a NASA project that has satellites in orbit, and they've been in orbit since 2000. And there are a number of satellites with sensors, and they're measuring all kinds of radiative fluxes coming from the Earth and also coming towards Earth. In other words, the shortwave radiation coming from the sun, and all the long-wave radiation fluxes, and also cloud cover and other things coming out of the Earth, right? So the difference between the absorbed solar radiation and the outgoing thermal radiation is the quantity called Earth's energy imbalance, and that difference turned out to be positive. And so the graph on the left, it shows the anomalies of the absorbed solar radiation and the outgoing long-wave radiation. You can see that they're both increasing, but the rate of increase is quite different. The absorbed solar radiation by Earth has been increasing at a rate of about 0.8 watts per square meter per decade, while the long wave radiation, cooling of the Earth has been increasing only at a rate of 0.3 watts per square meter per decade. The graph on the left, it shows the absolute amount of the energy imbalance as calculated by Cirrus, and it has an overall trend of about half watt per square meter per decade increase. Now, in climate science, this is considered now a big deal. This energy imbalance, which the MIT website called radiative forcing, and that's another name for it, but this energy imbalance is currently viewed as the most fundamental indicator of climate change. And why is that? Well, it's because it is believed that this energy imbalance is a result of trapping heat by the Earth's atmosphere because of the increased concentration of greenhouse gases due to human carbon emissions. Okay. And this is an excerpt from our paper on the left. This is why I'm encouraging you to look up our paper. It's about 30 pages, but has a lot of very interesting information there with citations and everything. It's a technical paper, but most of it is understandable on a conceptual level. So this is an excerpt that actually describes the Earth's energy imbalance and how it is treated by IPCC and the current, the mainstream climate scientists. So they have calculated that this energy imbalance is positive and has been positive for several decades, okay? And so the assumption is that this is the result, like I said, it's a result of trapping of heat by increasing concentration of greenhouse gases, and therefore they expect that this heat is accumulated somewhere, and this somewhere is below the surface. And the calculations of the IPCC talk about accumulation mostly in the oceans. They estimated about 90% of this trapped heat in the troposphere, because of greenhouse gases, gets sent into the oceans and accumulated in the ocean. About 8% or so is accumulated in glaciers and the continents, and only 1 or 2% remains in the atmosphere. Imagine that. Now, anyone who understands atmospheric physics a little bit, reading that stuff will say, wait a minute. So the trapping of heat occurs in the troposphere, in the air, and we know that all net fluxes in the troposphere are directed outwards, they're directed upwards. In other words, they're away from the surface. How is it, and what is the mechanism that 98% of this heat trapped in the troposphere ends up in the subsurface of Earth, mostly in the ocean? How that happens? Well, there is no explanation in the literature. There is absolutely no discussion about that. They just said that the heat was trapped in the ocean. Why? Because they see, based on the measurements of the ocean temperatures, and the ocean temperature, because the ocean heat capacity is so huge, they're talking about very, very small, minute changes in ocean temperature. For example, over a period of, 50 decades, you may have a difference of 0.2 or 0.3 degrees Celsius in the ocean column of 2,000 meters, like from the surface of the ocean down to 2,000 meters. Very small change in temperature. How they measure this so precisely, it's a different story, and I'm not going to go into that. But they use that supposedly empirical observations to calculate the heat content of the ocean. And then the heat content is the one that they think this accumulation of heat, because they see this increase of accumulation of heat over time, it's coming from the trapping of heat by greenhouse gases in the troposphere. Huh? How that works? Well, the IPCC integrates this energy imbalance not only over space, but also over time. And they end up with some astronomical numbers that are measured in zetajoules. Now, 1 zetajoule is 10 to the power of 21 joules. You could not even say, there is no other name than a zetajoule. They have those Greek letters that they use for different, large numbers, right? So zeta means 10 to the power of 21. That's a huge number, right? But because that's integrated over time, like, for several decades and over the entire globe. And then you have publications like the one on the left here, on the right, I'm sorry, that compares this accumulation of heat to, 20, what was it, the number here? Billions of atomic, 25 billion nuclear bombs. So the Earth, you see, the Earth has been accumulating this heat, 25 billion nuclear bombs over a period of several decades. And this heat is being stored into the ocean mostly. And it's just a matter of time. One day it's going to show up on the surface, and then the hell will break loose, right? And we don't know when this is going to happen, but in several decades. And that heat that has been accumulated will guarantee the continuous warming of the planet, even if we, cancel all the carbon emissions and, we kill ourselves entirely, basically. And, there is no human carbon emissions. This heat will, once it starts coming out, it'll go for centuries. That's the idea, right? So, just reading this, people who understand a little bit of physics have so many questions. Like I said, the first one is like, how in the world this trapping of heat, even if it happens, and people, engineers and so forth that work with this stuff, they know that open system cannot trap heat. If you don't have a roof on something, you cannot trap heat. The atmosphere has no roof, right? So how this trapping of heat can actually be transferred from the troposphere into the subsurface. Like 98% of it goes into the subsurface and only 2% stays in the atmosphere, right? So, okay, I'm just giving you this as an example, how far this confusion about what the Earth's energy imbalance means, how far this confusion goes, and what are the implications of that for understanding the climate system, or rather misunderstanding the climate system. So let's see what this energy imbalance is all about. Okay, the first thing is, this is a result from the Cirrus data in magenta, and it shows the outgoing long-wave radiation as measured by Cirrus at the top of the atmosphere. The curve in red, it shows the variations in global surface temperature, and this is the average of 6 global databases. This is also in our 2024 paper. And what this graph shows is that those are 13-month running means. So each value, each point represents kind of about annual average, right? And so it shows that the two curves are totally in phase. When the temperature goes up, so does the outgoing flux on the top of the atmosphere. And when the temperature goes down, so does the outgoing flux. So the fact that they're in phase, it tells you that there is no trapping, at least beyond a year, let alone accumulation of heat for decades, right? So because if there was a trapping of heat, those curves should be out of phase somehow, and they're not out of phase. They're in perfect phase. So within a year, the temperature response on the surface that is caused by something, in this case is actually the increase of amount of shortwave radiation absorbed from the sun because of the decreasing albedo. The temperature fluctuates, and this temperature fluctuations causes a surface flux, which finds its way to the top of the atmosphere in form of long-wave radiation, and that's what the satellite measure, okay? So let's look at the relationship between energy imbalance as measured by Cirrus and global surface temperatures on one hand, and energy and the absorbed solar radiation also measured by Cirrus and global surface temperature. So the graph on the left is the relationship between this energy imbalance, which is viewed as the most important indicator of climate change, and actually the driver of climate change itself, right? They're not saying just indicator. They say this is actually what's driving the system, because they think this energy imbalance, is something that accumulates inside the system, right, over time. So here the correlation between the global temperature and the Earth's energy imbalance is only 0.36. That means the energy imbalance statistically can explain only 36% of the temperature variation. On the other hand side, the graph on the right, it shows the correlation. This is just statistical correlation, right, between absorbed shortwave radiation from the sun because the albedo has been decreasing. The cloud cover of Earth has been decreasing over the last 25 years, and you have increase in the amount of absorbed solar radiation. So this is the absorbed solar radiation global temperature, and the correlation is almost 0.8. So that statistical comparison alone tells you that obviously the shortwave, the change in the absorption of shortwave radiation of sunlight is more important, explains a lot more than the energy imbalance, right? Now, here is the actual statistical comparison. So on the left, we have the energy imbalance and global temperature. The scatter plot on the lower left shows basically, in form of individual points for each month of this period of 24 years. It shows the relationship between Earth's energy imbalance and the global surface temperature. And like I said, the correlation is 36%. So in other words, this energy imbalance only explains 36% of the changes in the global temperature. On the right, we have a results from a model that I'll present here in a minute, but it is described in our 2024 paper, a model that only relates the changes in absorbed solar radiation or changes in albedo and total solar irradiance, which is the solar constant at the top of the atmosphere, takes those into account and calculates what would be the change in temperature on the surface given the observed changes in those variables. And what we have here, we actually see that this model produces a curve, a temperature curve that is very close to the one that is observed, so much so that the model completely explains the total warming trend over this period of 24 years. And the graph on the lower right, the scatter plot, it shows the correlation between observed global temperature anomaly and modeled global temperature anomaly. And the correlation is 0.83. In other words, the model that only takes the effect into account, the effect of decreasing albedo, observed decrease in albedo, and observed changes or slight variations in the solar constant, it's capable of explaining 83% of the interannual variation of the warming for the last 24 years, and 100% of the total trend. Okay? That implies that there is no signal from CO2 or any other greenhouse gas or any anthropogenic radiative forcing in recent warming, in the warming of the 21st century. Not only that, but it also implies that there are no positive feedbacks, because in the model that I'll show here in a minute, this is the equation in the middle of the screen, that model has no positive feedbacks in it. It's just a objective derivation of a relationship between surface temperature change and the change in the solar constant, so-called solar constant, which is called also TSI, a total solar irradiance, and the change in albedo delta alpha. Okay, this equation is derived. The derivation of this equation is shown in details in our paper, 2024 paper. And the paper goes through a lot of details, so I'm not going to explain this here. I mentioned this, I think, in the previous presentation that I did in December. But here, basically, on the left, you have the two inputs to the model, which is the observed changes in albedo, which is the gray line here, 13-month moving average of the albedo. And as you can see, there has been a significant decrease in the albedo, which is the reflectivity of the Earth. Most of this decrease is due to the drop or decrease of the cloud cover, specifically low-level clouds. And then the graph on the graph below that, it shows the variations in the total solar irradiance or in the solar constant. Now, those variations hardly have any trend, maybe slightly increasing, but it's very close to zero, but they fluctuate with the solar cycles, 11-year cycle of the sun, that is well known. So those two things are included in this model. The albedo delta alpha variations in the second term here in delta alpha, and the delta S is basically the change of the variations of the total solar irradiance, and the result is the model here on the right. I'm sorry. So now let's look at the model that we have developed in our 2024 paper. It has an equation that also relates directly the change of absorbed solar radiation to the global temperature. This equation, because it's generic, it can be inverted and can be solved for the energy flux, and then it can be applied with actual observed changes in the global temperature to calculate the energy flux that this global temperature will produce at the surface, not in the top of the atmosphere, but at the surface. Okay. So we saw on the previous slide that the variations in the global temperature actually 100%, 83% explained, internal variations, they explained by the change in albedo and the TSI. And basically, those changes in temperature, they induce a surface flux. So this surface flux is given by this equation here. And one can calculate the surface flux, which is given here in dark red, looks like brownish almost. And this flux is compared, which is the flux of the surface, is compared with the flux at the top of the atmosphere measured by Cirrus. Okay. And you can see that the surface flux has a much steeper trend. The trend in the modeled energy flux of the surface is 0.76, almost 0.8 watts per square meter per decade. And the observed long wave flux at the top of the atmosphere by Cirrus is only 0.3 watts per square meter. So those fluxes are clearly different, in terms of trend. The phase is very similar. The phase is the same because they're both driven by the surface temperature, right? However, if you do a scatter plot of those two fluxes, and we have on the x-axis here the modeled outgoing total energy flux at the surface, and on the y-axis we have the outgoing radiation, long-wave radiation observed by the satellites, we get the scatter plot, and the relationship between modeled and outgoing observed is actually a ratio 0.479. This is almost the exact ratio that we found in the IPCC diagram, energy diagram of the Earth, where was the ratio of the total flux at the top of the atmosphere divided by the total flux at the surface. So we had 239 divided by 501, and the result was 0.477. Here, we get a ratio that is 0.479, almost identical, right? So what that means is that we have attenuation by the same token, the same process that attenuates the total flux from the surface to the top of the atmosphere, to the top of the troposphere. That same process attenuates also the change of the surface flux that is induced by variations in the shortwave radiation, absorbed amount of shortwave radiation by the Earth. And that attenuation of that surface flux is basically the same magnitude as the one that we see the total flux in the IPCC diagram. Okay. So when you apply the coefficient, the Tfac, which is the tropospheric energy flux attenuation coefficient of 0.477, the one that was inferred from the IPCC diagram, you apply this and you multiply the modeled surface flux that we just showed on the previous slide. Here is shown also in dark red. You multiply this and then you compare to the actual observed cirrus flux. You see that the two fluxes now collide. They're basically the same, right? So that tells you that, and also furthermore, we can do the same thing with two observed fluxes. If you look here on the left graph, you have the absorbed solar flux by Cirrus and the observed long wave flux by Cirrus outgoing. And on the right graph, we have the same two fluxes, but the absorbed solar flux has been multiplied by the Tfac coefficient. Okay, and you see that causes the trend of the two fluxes to be very close to each other. So that tells you that the so-called energy imbalance is basically a result of adiabatic cooling of the outgoing or the ascending convective currents as they go through progressively lower levels of pressure in the troposphere. And it's a process that has nothing to do with the absorption of long-wave radiation or absorption of heat by so-called greenhouse gases. None. Okay, I guess we got to the conclusions. So first of all, the vertical attenuation of surface energy fluxes throughout the troposphere is a result of pressure-induced adiabatic cooling that is unrelated to the atmospheric infrared opacity induced by so-called greenhouse gases. Second, the Earth's energy imbalance is an apparent phenomenon that arises due to adiabatic dissipation of thermal energy in ascending air parcels in the troposphere caused by a decreasing atmospheric pressure with height. This implies that there is no greenhouse gas radiative forcing in reality. So basically, the definition of the greenhouse effect and the definition of radiative forcing through the Earth's energy imbalance are based on energy that is not there, non-existing energy, because it has been dissipated. And this is actually the next conclusion. Integrating Earth's energy imbalance over space and time in an effort to calculate the energy gain by the Earth system, as done by researchers in recent years, is physically meaningless because the imbalance counts energy that is adiabatically lost in ascending convective currents. Hence, the Earth's energy imbalance does not represent heat accumulated below the Earth's surface that would be released in the future to cause additional warming as currently believed. It is true that the Earth has but has gained heat. It has become warmer. If you have a higher temperature, of course, the Earth has become warmer. But this warmth is because of the increased, consistent, and sustained increase of absorbed solar radiation by the planet. That's what has caused the Earth to be warmer. It's not the trapping of heat by greenhouse gases, right? Lastly, the Earth's energy imbalance results from a varying sunlight absorption by the planet and would only disappear if the Earth's albedo would stop changing and the uptake of shortwave radiation stabilizes, which is unlikely to occur ever. So there you have it. So basically, here I want to point something. This is a little bit outside of science, but given this evidence that there has been a profound misunderstanding of such a basic observation, basic phenomenon, which is the attenuation of the surface energy flux between the surface and the top of the troposphere. This profound misunderstanding that people think, or the climate scientists think, including skeptics, that this is caused by greenhouse gases. And given the fact that these definitions are physically void, they're meaningless, they're just pointless, I see the need here for fundamental revision of climate science. And I believe, from my own personal experience, that this revision will not happen because scientists across the board will have an epiphany about what's happening, and they will correct, their understanding, they will correct their models and so forth. This is not going to happen unless and until there is a change of funding. So this is a very harsh reality, and our President Trump is now implementing measures in other areas along those lines. But basically, the idea is that if you want to make people to behave certain way, it's unlikely that they will change their behavior because of some insights that they get all of a sudden or some epiphanies that they get. It has to be economic leverage, economic tools applied in order to change the people's behavior, or the people's, in this case, to change the focus of science in directions actually that are meaningful, physically meaningful, and that actually can bring results, as opposed to focusing on something that is non-existing, like the greenhouse effect, a radiative greenhouse effect, and Earth's energy imbalance, right? So I'm making here an appeal to everyone who is watching this video. If you have any questions, communication with the Trump administration and so forth, we would like to have the opportunity to present this new science to, to the new political leadership of this country, because I believe that unless there is a moratorium on funding on any CO2-related climate research, there will be no change in science. We have to change the funding. That means we have to cancel, we have to eliminate the funding that goes in direction of supporting CO2-related climate research, because that's a dead end. It has been dead end for decades. So there you have it.
What do you think in the big picture causes these cycles of glaciation? Do you think that it is big fluctuations in the mass of the atmosphere, or is it Milankovitch and the atmosphere stays pretty much with the same mass over time?
So I addressed this issue very, not in details, but I think I addressed it well in the previous presentation. And our research has shown, and this is based on numerical evidence, it's not based on some theory or some thinking, it's based on numerical evidence, which is basically the ability of a model to reproduce the so-called polar amplification, which is basically a phenomenon where the changes of the temperature of the poles have been always larger than the changes of temperature of the equator. And this polar amplification is visible during the ice ages very well. The polar temperature through the cycles of ice ages have been changing like 4 or 5 degrees, between 4 and 6 degrees, I would say, average about 5 degrees. While the polar temperature, the equatorial temperatures have been changing about 5 degrees on average. The polar temperatures have been changing around 12 degrees on average, right? So that's a clue. If you have a model that can reproduce that seamlessly, that model should give you an insight what may be the driver of the ice ages, right? Specifically. And what we have found with our analysis is that the only way to reproduce very accurately, actually, those changes are if we assume that the pressure or total mass of the atmosphere has been the driving factor of the ice ages, meaning that there has been fluctuation of pressure in the order of 30%. So the pressure from about 1 bar going down to about 0.7 bars or 0.69 bars, and then going back to 1 bar, maybe a little bit 1 bar above the 1 bar, which was the previous warm period, Emission, 125,000 years ago. It was warmer by about a couple of degrees, and we estimate that's about something like a 10% or so higher pressure than we have today. So, but yes, our conclusion is that it has to be, I mean, we went through the logic and the physics of all that. The numerics do not work any other way, except that you have to admit and realize that there has been a change in total atmospheric mass and surface pressure, which has been driving warm periods and ice ages, in alternative cycles, which actually, it begs the question, what is the cause for that? And we don't have a clear answer, simply because the topic of changes of atmospheric mass and pressure has been almost studied zilch, nothing in climate science. I mean, we don't have any proxies for reconstructing pressure. No one in paleoclimatology talks about pressure changes on this time scale. It's not in the thinking. If it's not in the thinking, then of course there has been no research to study changes in pressure, right? Because everybody assumed that the pressure was the sign, and they're focusing on CO2 as a driving force, which is total nonsense. But yeah, interesting enough, if you take the CO2 from the climate models as a radiative forcing, climate models become absolutely unable to explain the ice ages, not even close, even if they implement fully the known Milankovitch cycles. And I have a blog article that I put out a couple of years ago that shows the relationships between ice ages in terms of changes in global temperature and different parameters of the orbital cycles, and the correlations are known there. It's like almost no correlation. It's like the highest correlation is 0.3 or something. I mean, it doesn't exist. All the other correlations are less than that. So there is no evidence at all that Milankovitch cycles had anything to do with the ice ages, numerically speaking. That's the long answer to your question.
Is there any change in the mass of the atmosphere that we could possibly measure over the course of like 50 years or something? Or would that be a very, very slow change?
I think probably not, no. I think that the changes that we have reconstructed from the geological record shows that significant changes in the atmospheric mass likely occurs on timescales of many thousands of years. And now we are in a Holocene, kind of a relatively stable climate. We have been in a kind of a cooling period since the last 4,000 years or so, but it's very slow and probably will take another 5,000 years before we start sliding down into the ice age, And it takes, tens of thousands of years to get to the bottom of the ice age and get out of it, So it's a long process. The only way is to come up with proxies, reliable proxies, and I think they probably exist. It's just nobody has been looking for them. Proxies of pressure that could be applied to the paleo record to reconstruct pressure in an objective way. The same way we have proxies for temperature, for example, right?
Okay. Any final points you'd like to make before we finish up?
Well, I'd like people to start really thinking seriously about what we have discovered, and especially this presentation is something that is based on standard atmospheric physics, something that you can find in textbooks. And to me, it's beyond my belief and understanding how come people with Ph.D. degrees would be confused on such a basic level about atmospheric thermodynamics and not understanding what's causing the drop of temperature with altitude in the troposphere, and of course, related to that is the drop of thermal energy in the troposphere, and that's the decrease in pressure. I mean, it's a standard stuff. The equation that I presented here, that they can be found in any textbook. And yet, we have people in climate science that think that the radiation is everything, and they try to explain the lapse rate with radiation, and they tell stories that are physically absurd. That without greenhouse gases, we'd have isothermal troposphere. I mean, it's beyond belief in my view.
Okay. On that note, we'll wrap up. Thank you very much, Ned. We'll talk to you next time.
Thank you.
Appreciate it. Talk to you soon.